Hi, this is Parnia from SkyWatch, and today we're going to talk about how we integrate artificial intelligence solutions to solve challenges in satellite imagery. The agenda of this presentation is as follows. First, a brief introduction of our company. Second, describing the challenge we want to tackle. And third, our solution to this challenge. Fourth, a demo of our results. And last but not least, our future plans to enhance the solution. Let's start with the introduction. Here at SkyWatch, we are on a mission to make satellite data accessible to the world. With new applications for this data being discovered every week, the demand for this imagery is increasing across many industries. However, the current process for purchasing satellite imagery is tedious and time-consuming. We want to make sure it is easy for you to monitor the progress of crops, predict the markets, track ships and airplanes, measure global warming, or create other game-changing applications. Our goal is to be the leading provider of data and intelligence from space. Now, let's define the problem we want to solve. Satellite images taken from the Earth are sometimes covered partially or fully by clouds. This is not ideal as they cover the areas of interest on the surface of the Earth. So when a customer orders an image, if it is obstructed by clouds, they will return the image for a refund. This is a tedious process for both the customer and the company. We use the terminology of cloud mask to refer to the area in the image that is covered by clouds. The problem is how we detect the cloud masks on satellite images. This way we can automatically discard the images in which the area of interest to the customer is covered by clouds. Conventional methods for detecting cloud masks are often inaccurate. Here is a sample. On the right you can see an image from shoreline. On the left you can see the corresponding cloud mask in which the white pixels show the cloud and the black pixels show the background. You can see that the waves close to the shoreline are mistakenly detected as clouds. Let's see another sample. On the right you can see an image fully covered by clouds. On the left, the cloud mask produced by another conventional algorithm is shown. As you can see, the cloud masks are incomplete and the clouds are only partially detected.
Hi, my name is Elaine and I'm going to present our solution. Here is a diagram of our system. On the left-hand side, we got multispectrum data from band 1 to band 7, which are in the visible and infrared portion of the spectrum. Most color images consist of RGB bands, namely red, green, and blue bands. And here we also include the near-infrared band, shorthanded as NIR. This band is commonly used to classify healthy vegetation. However, as we discover later, the RGB bands are the most important in classifying clouds, since it contains the spatial pattern of the cloud. After we have prepared our input image, we feed that into our deep learning segmentation network. This network will look at the input image and extract features from it and classify each pixel as either cloud or non-cloud. As you can see from the right-hand side, it's the prediction from our model, the cloud mask. To summarize our solution, we have developed a deep learning algorithm to predict clouds, shadows, and zero-value pixels, aka the invalid pixels. We train our model on a variety of data, including open source data and also SkyWatch commercial datasets. By doing this, we ensure that our model can generalize well on most types of data. Next, I'm going to show you some results from our solution. We call our model raw product prediction model just because it takes an input of RGB plus near-infrared band, as opposed to just RGB-only images. And we tested this model on images on Planet and CCA. Both are open source datasets, and also our SkyWatch commercial dataset, and we achieved 94% pixel level accuracy. On these slides, we've got some results from our experiments. On the left-hand side are the raw images from our test data. And on the right-hand side, we got some predictions from our own model. As you can see, the blue color represents the clouds, red represents the shadows, and black represents the clear background. Our model successfully detects both popcorn-style clouds as well as very thin clouds. Looking forward, since we've prototyped a pretty good model and it shows some promising results, our next step is to deploy this into production. In order to do that, we will need to reduce the current inference time and also improve scalability when the traffic spikes. Meanwhile, we are working to develop a preview prediction algorithm. It's a similar algorithm but works only on RGB-only images. And the goal for that is to run the cloud detection algorithm on a low-resolution thumbnail to improve fulfillment and decrease costs before we ever order an image for our customer. Last but not least, when new data providers come in and the data distribution has deviated significantly from our training data, we will need to label our new data and retrain the model to ensure accurate results. That's all. Thanks for watching.